So in question number 4, it's asking you to consider the answers that you got for a few specific parts in number 3, namely A, B, G, H, and J. I went ahead and wrote my answers here just to make sure that you have something to refer to, but hopefully you've taken the time to check the answer key and verified those answers for yourself. It wants to know in letter A what they all had in common. And if you just look at the values themselves, we probably don't see a lot of commonalities. I mean, 20 doesn't have much to do with 1/2, which doesn't have a whole lot to do with 2/9 or 6 or 9/2. They don't have any common values or structures. I mean, they're all technically real numbers, but it's not like they're all fractional or anything. But if we dig a little bit deeper, hopefully you noticed one thing. 20 was the initial value of expression A, and 1/2 was the initial value of expression B. 2/9 was the initial value of expression G, 6 was the initial value of expression letter H, and 9/2 was the initial value of expression J. So it is not coincidence that all of the answers that you got to those questions happened to be the exact same answer that you wrote for the initial value. And even when you got to the questions where you didn't even have to write the initial value anymore, you can still make that connection. In letter G, oh yeah, the initial value was 2/9. In letter H, the initial value was 6. In letter J, the initial value was 9/2. So that is a commonality. And while I will not write that in the blank space, hopefully you can write it for yourself and use my words. Of course, you can pause the video to give you time to help you digest the idea. All of these have in common the fact that the answer was the initial value. Now in letter B, it's really asking us why. Like, if all it was giving us was the initial value, I mean, that's cool. We probably should have realized that, but like, what mathematically is making that possible? Like in letter G, I should say, 2/9 times 6 to the power of 0. We're saying that the answer to that expression is 2/9. How could that be mathematically possible? Why? Mathematically, not because of the sequence, but why? Because of the order of operations, multiplying and exponentiating. Why is the answer 2/9? Why does multiplying by 6 to the power of 0 not seem to be changing this 2/9 at all? Some of you may be remembering now a rule that you could have learned maybe back in your first algebra class, maybe even before that. And that's the idea that when you multiply by something like 6 to the power of 0, or anything to the power of 0, we're really saying, well, it's 2/9 times something, and it's going to give us 2/9 as an answer. Mathematically, well, what could we be multiplying by? To essentially make something unchanged, we would say, oh, well, 2/9 times 1, that's the only thing I could multiply by that doesn't change the 2/9 at all, which leads us to believe, by essentially substitution, that 6 to the power of 0 must have a value of just 1. Because multiplying by 6 to the power of 0 wasn't changing my 2/9, and the only way we can infer that is because if 6 to the power of 0 is 1, then that's the only thing that makes sense. But how could that be? 6 is clearly a bigger number, and yet 6 to the power of 0 is 1. What? And if now you're like, wait, no, Herbert, I've learned this rule before. This is a rule of exponents. That's actually true. Anything, any base, like 6 or any other number to the power of 0, really is equal to 1. And this is one of the major reasons why. It's one of those rules that sometimes we learn in middle school or in Algebra 1 and we just memorize and go, okay, well, that's the rule because my teacher said so or my textbook said so. But actually, this is part of the reason why. Is because the 0 term is the initial value, which means the multiplier hasn't taken effect yet. So it's essentially saying, hey, yeah, we've got this sequence with an initial value of 2/9 and a multiplier of 6, but hey, don't start multiplying yet. You're still at the 0 term. You don't have to multiply by 6 yet. Don't do anything yet. Just hang out at the initial value for a second. That's actually what this rule goes back to. It's like saying anything to the 0 power, we haven't started multiplying yet. The power is the number of times you're multiplying something. So if this says, hey, don't multiply anything, multiply nothing, 0 means nothing. If this says, hey, multiply by nothing, then we're at 2/9, not multiplying by anything. My answer is going to stay 2/9. So that's why anything to the power of 0 is 1. is because it's like saying, hey, multiply by 1, don't do anything. Remember how multiplying by 1 doesn't do anything that you can see? Multiplying by 1 doesn't change anything. That's what this sequence notation is telling us. It's saying, hey, start at 2 ninths, but don't go anywhere yet. Don't start multiplying anything yet. And that's why anything to the power of 0 is 1. Now, there are actually lots of other reasons why as well, and maybe in your Algebra 1 class or in your 8th grade or middle school classes, they would have taught you another reason why anything to the power of 0 is 1. There are actually lots of different reasons. Some people learn it because of another rule of exponents that has to do with subtracting. Some people just memorize that rule and they don't really know why, they just know that it works. And some people learn other rules that have other properties. And we'll get into all of those things. But if you knew this fact and never really knew why it was true, hopefully understanding sequences helps you understand why it's true. But the takeaway message, if I was to say, highlight one thing from this video that is super important, it's this fact right there, that anything to the power of 0 is always going to be equal to 1. That actually I would put in my answer for letter B. Anything to the power of 0 is equal to 1. And I would make sure that I understand that idea so that when you get into the next questions, like question number 5, we have an idea of what that means. Because when I say anything to the power of 0 equals 1, that means if I have any part to the problem, like in number 5, letter A, this is 3 to the power of 0, that 3 to the power of 0 is going to substitute with a 1. Now that doesn't change the 6 to the power of 2. That's almost like an initial value or something where it's like, yeah, that's happening. But 3 to the power of 0 is saying, whoa, pump the brakes, don't do anything over here. So I'll do 6 squared. 6 squared is 36. But 36 times 1, like don't do any other multiplying. Multiply 0 other terms. Multiply nothing else. That's like saying, well, do 6 squared and then don't do anything else. 6 squared is 36. 36 times 1 just remains 36. So that's the idea with this thing to the power of 0. It's like saying, hey, pump the brakes. Don't do any more multiplying here. That's what exponents really are. They're telling you how many times to multiply. That's why like a square means multiply something twice. A cube means multiply something 3 times. Power of 0 means multiply something 0 times. Don't multiply at all. And that's why in letter B we could use a little bit of common sense. Letter B says, okay, do 15 squared. That's a big number. That's like 225. And multiply 2 cubed. 2 cubed is 8. But then it's saying, okay, yeah, take that big answer, whatever that is. That's a huge answer. 225 times 8. I mean, I'm going to use a calculator for that because I don't even know what that is. 225 times 8 would be 1,800. So I have 1,800 to the power of 0, which is like saying, hey, stop multiplying. 1,800 to the power of 0, don't multiply anything. Anything to the power of 0 is 1. And that's where I should stop and say, dang, I just wasted my own time. I didn't need to know what 15 squared was. I didn't need to know what 2 cubed was. I definitely didn't need to multiply them together because I realized, hey, wait, this whole thing is telling me don't multiply anything at all. Don't multiply anywhere. It's all going to be to the power of 0 anyway. So you can use some common sense strategies here, and you can use this anything to the power of 0 strategy to help you take some workarounds and some shortcuts. In any case, try this row, but try to do them without a calculator so that you can practice incorporating this idea that anything to the power of 0 is 1. You don't have to think of them like sequences anymore. If the sequence thing confused you and you're like, Herbert, did I really just watch 4 videos just so you could tell me that anything to the power of 0 is 1? I already knew that. Then, yeah, cool. Use the fact that you already know. I don't want to have wasted your time, but I do want to have given you some context for why that rule is what it is. It's cool if you knew that rule, but the hope is that you knew why the rule was. So, in any case, try number 5, and once you feel like you get it, then we'll look at the next rule of exponents that you may have already known to see if that helps you connect another idea.